Hello, my name is Isaac Edminster, and I, along with Julio Lopez Hernandez, Andy Wong, Benedict Matveev, and our advisor Dr. Young Bok Kang, have been researching the question, how might we create a comfortable, easy-to-use method to detect electrical signals in response to muscle pain? In September, we identified a problem that many of us face on a regular basis, lower back pain. Lower back pain exists because of contractions in the muscles, which give off electrical signals that can then be detected via an electromyography sensor. Lower back pain is a widespread problem among American citizens. According to a 2014 survey done by the CDC, as many as 29% of adults experience lower back pain. That number rises another 5% when we only focus on the elderly. One current product that partially seeks to solve this problem is the MyoAware muscle sensor for Arduino. This device, while functional, requires both knowledge of Arduino along with one-time use sensors to detect muscle signals. Because of this, we feel as though its uses are limited. Another potential solution is that of invasive electromyography sensors. However, these sensors involve inserting a needle into the muscle to detect the signaling. We concluded that this, too, is not a reasonable solution for everyday use. Based on these products, along with other surveying and research, we found out that there is no low-cost, easy-to-use way to measure and monitor muscle pain. As such, we looked to design a product for these 100 million or more Americans that may suffer from back pain. As we brainstormed through the fundamental reasoning for the creation of our product, we decided on three primary characteristics that it must have. It must be durable, flexible, and easy to use. As we moved into our design process, we recognized that liquid metal would prove invaluable for making a flexible, comfortable sensor. We ultimately decided to use Galveston for its low toxicity, high conductivity, and low price. Another important aspect to this project was choosing the correct material to make the sensors out of. PDMS was chosen for its high durability, flexibility, and stretchability, with the added benefit of being cheap to produce. To ensure that the liquid metal was able to spread uniformly throughout the sensor, we created gradient channels by injecting 0.1 molar potassium hydroxide into the channels and running a current through them. This allowed the liquid metal to flow into the correct location. We wanted to ensure that the PDMS Galveston sensor was able to conduct charge in both flexed and relaxed positions. The sensor was able to do this well, as can be seen by the illumination of the yellow light. A MyoAware Arduino module was purchased and used to test both the capability of our market sensors, along with the standard EMG signal detection capability of a common market solution. This guaranteed we would have a control group to compare our solution to. We wanted to create potential circuits that we could implement with liquid metal into a wearable PDMS device. On the left is an amplification circuit that can be used with similar capability to the MyoAware sensor. On the right is a display circuit that shows the absolute signaling of a muscle at a given time. The display module is then presented here, with a flex muscle showing more bars on the display, while a relaxed muscle shows less. Beyond the circuitry of the wearable sensor, we have also been working on designing the detection capability of the sensors. These are two prototypes of the Galveston PDMS sensor that we synthesized. While both sensors worked, we wanted to focus on fine-tuning and increasing the sensitivity of each. As we look to the future, we want to work on implementing and merging the two major aspects of the project, the circuits and the liquid metal sensor. We plan to focus our efforts to integrate the circuits we have designed into a PDMS sensor using Galveston as the wiring. One potential use and the original purpose of our project was as a muscle pain detector. People could wear this device and find the primary causes of back pain, along with ways to resolve this pain. Because of the widespread nature of muscle pain, we believe the market for this product would be quite large. Another potential impact of our project that has arisen more recently is in prosthetics. Assuming we have a comfortable, straightforward way of detecting muscle flexing and signaling, this could be implemented into a smart prosthesis that acts very similar to a human limb, by detecting a muscle signal and moving accordingly. With the number of people with limb loss in America above 2 million, this triples our initial market and greatly adds to the viability of our solution. If we continue forward in this competition, we would use the money to further integrate circuitry into a PDMS sensor, along with exploring more potential uses in prosthetics. Thank you for listening.